All right, welcome to the Explainer. Today, we're going to peel back the curtain on something you do, well, literally every second you're using a device. We're talking about how our world gets translated into the secret language of machines. So let's just jump right in. Have you ever really stopped to think about what's going on when you hit a key on your keyboard? I mean, how does a machine that only gets on and off have any idea what the letter A is, or the color red, or even a character from a completely different alphabet? Yeah, every single time you type or click or tap, you're kicking off this super complex conversation. And today, we're going to break down exactly how that conversation works. So, for this whole thing to work, it all has to start somewhere. And it starts with a kind of secret code. It's like a universal agreement, a rule book that tells the machine what every single character actually means. Okay, so picture this. You press the A key. The computer doesn't see an A, not at all. To the machine, it's just a little blip of electricity, a raw signal. And that signal, well, it needs a translator, fast. And boom, instantly, that electrical blip gets mapped to a very specific number. In the case of a capital A, that number is 65. Now, this isn't just some random number they pulled out of a hat. It's all laid out in a foundational standard called ASCII. That stands for the American Standard Code for Information Interchange. You know, this whole process has a name. It's called encoding. And the easiest way to think about it is like a universal dictionary that pretty much every computer in the world has agreed to use. It's the reason why when you type an A on your keyboard, a computer on the other side of the planet sees it as an A and not, B or some crazy symbol. And ASCII back in the 60s was a total game changer. Seriously, before ASCII, it was kind of the Wild West. Different computers had their own ways of representing characters. They couldn't talk to each other. So ASCII comes along, uses a 7-bit system, and creates 128 unique slots. That was enough for the English alphabet, numbers, and some symbols. It created a common language. But, and this is a big but, it was really only built for a small, English-speaking world. Right. So as computers and the internet started to take over the world, it became super obvious that 128 characters just wasn't going to cut it. Not even close. We needed a much, much bigger dictionary. I mean, think about it. What happens when you need characters for Spanish or German, Russian, Hindi, the 128 little slots in ASCII? There was just no way that was going to be enough to handle every single character from every written language on Earth. So the problem was crystal clear. ASCII's 128 slots were just a drop in the bucket. The solution had to be huge, and that solution is Unicode. This thing is a beast. It's a standard designed to handle over 149,000 characters. Its whole mission is to give a single, unique number to every single character. Doesn't matter what device you're on, what operating system, or what language you're speaking. Honestly, Unicode is kind of the silent hero that makes our global internet even possible. It's the reason a web page written in Japan shows up perfectly fine on a screen in Brazil. It is the universal translator, working behind the scenes 24/7. Okay, so we've got our letters turned into numbers. A is 65. Awesome. But we're not done. Not by a long shot. How does the actual hardware, the silicon chips and tiny transistors inside your computer, how does it understand a number like 65? Well, this is where we get down to the computer's native tongue. See, computers don't think in tens, like we do. They think in twos. Their entire universe is built on billions of microscopic switches that are either on or off. That's it. And we represent those two states with just two digits, 1 and 0. And that, my friends, is binary. And this is the final crucial step in the translation. The letter A becomes the number 65, which then gets converted into the binary number 10000001. That is what the computer's processor can actually understand. That's what A truly looks like to your machine, just a string of ones and zeros. Now, that's fine for one letter, but as you can probably guess, it gets really complicated and really, really long for us humans to read. So what happens when you have more than just one letter? What about a simple word? Just look at this. The word data, just 4 letters, becomes this ridiculously long string of ones and zeros. Now, for a machine, this is perfect. It can process this in a flash. But for a human programmer trying to debug this, trying to find one little mistake in that sea of digits, it is an absolute nightmare. Okay, so if binary is such a pain for humans to read, how do we deal with it? Obviously, people needed a better way, a more compact, human-friendly shorthand. And that's where hexadecimal comes in. It's this really clever system that acts as a perfect shorthand for binary. Instead of base 2, like binary, or base 10, which we use every day, it's base 16. So it uses 16 unique symbols, our familiar numbers 0 through 9, and then it borrows the letters A through F to represent the values 10 through 15. Now here's the really cool part, how it works. It's actually pretty elegant. Since 16 is just 2 to the power of 4, you can represent any group of 4 binary digits with a single hex character. So you can take a ridiculously long binary number, chop it up into little chunks of 4, and convert each chunk. Suddenly, that huge string from before becomes just 4 easy-to-read characters, C0F1. Way better, right? And listen, this isn't just some abstract thing that only programmers care about. You actually see and use hexadecimal all the time, every single day. You probably just don't realize it. For sure, one of the most common places you'll see it is with colors on the web. Ever seen a color code that starts with a hashtag like hashtag FF000? Yep, that's hexadecimal in action.
See, every color on your screen is just a mix of red, green, and blue light. And that hex code is a fantastic shorthand for it. The first 2 characters tell you how much red, the next 2 tell you how much green, and the last 2, well, you guessed it, blue. So FF means all the way up, and 00 means none at all. It's a super compact way to represent over 16 million different colors. Imagine trying to write out a 24-digit binary number for every single color instead. No thank you.
So let's recap the journey. It's this constant multi-layered translation happening completely behind the scenes. Your finger hits a key, an encoding standard like Unicode gives it a number. That number gets converted into binary, just ones and zeros, for the computer to understand. And then, for us humans, that long binary string often gets represented in a neat shorthand like hexadecimal. It's this whole process that takes our rich, colorful, complex world and boils it down to this simple on-off language that machines speak. You know, it's pretty amazing to think about what this is all built on. Every single step we just walked through, from a letter to ASCII to binary to hex, it's all just different ways of using number systems. All of our cutting-edge, incredible technology is resting on these ancient and frankly brilliant mathematical ideas. And this invisible system, this hidden architecture, is what lets us communicate with anyone, anywhere, in an instant. It's the absolute foundation of our digital lives. So the next time you type a message or just look at a color on your screen, think about that. And maybe ask yourself, what other secret codes, what other hidden layers of translation are hiding right there in plain sight, making it all possible?